Today I'll present PowerMan, an out-of-band management network embedded in the power system of data centers. And we do this by using power line communication. And this is work done in Hong Kong USD. I'm Chen. This is joint work with Jiacheng Xia, Bairen Yi, and Chen. So data centers. Data centers are the essential infrastructure of our time. And a typical data center will contain tens of thousands of devices, including the servers, switches, storage units, etc. At this scale, delivering management traffic is a challenging task. So data center management tasks include device installation, bring up, restart, configuration, diagnostic, and maybe some SDN applications. So for many management tasks, network is usually not the bottleneck, but the robustness and availability of management network is vitally important. So in existing data centers, the management traffic is usually delivered in-band with the data plane traffic. But this introduces the issue called fate sharing between the data plane and the management plane. So the failures in the data plane will actually cut off the management traffic to the exact locations experiencing the failure, so that it is impossible to perform important and relevant tasks such as diagnostics and recovery. So the first requirement for a management network is that it should always be available and should survive failures in the data plane and should be always ready to perform relevant tasks. So for these reasons, an out-of-band network is desirable for the operations and management of data centers. The out-of-band network also needs to be scalable so that it can reach every device in the data center. We can definitely use the same technology as in the data plane, and we build a replica network using electrical or optical switching. But this is going to be costly to do, and it will be also exposed to failures like the power system going down. So in recent years, the new networking technologies are being introduced in the data centers, such as 60 gigahertz wireless radio and free space optics. As an out-of-band network, if they want to do so, for a full coverage of the data center, they need to install reflective surfaces on the ceilings or on the wall or do signal relaying. But doing so will not be compatible with existing data center designs. For example, we need to change the room interior to install the mirrors, and we need to enforce ceiling height clearance so that the signal can propagate better. We need to change the rack dimensions so that we can fit in the antennas and transceivers. And we need to have some regulations on the inter-rack distance so that the signal can be relayed better. And more importantly, some of the devices are kind of costly. But without this kind of technologies, how do we build a robust and scalable and easy to deploy data center management network? So we take a step back and ask a more general question. And how do we build a robust and scalable system? And how hard is it? And we all know that the answer is that it's really hard. We need to integrate enough redundancy so that we can survive the failures. We need to design mechanisms so that we can fail gracefully when the failure happens. We also need to compartmentalize or isolate the failures. And when a failure occurs, we want the replacement and repair to be really easy. And there are many more boxes that we want to check. And whenever we build a new system, we need to check all the boxes again. But the question that we are going to have is that do we really have to? And we believe that in some cases, when there is already a system that is robust and scalable, we can try to borrow these properties rather than building the entire system from scratch. So what is such a system in data centers? The most robust system in data center is the power system. From left to right, it consists of the main switchboard, which directs the power from the energy sources to the different smaller load regions, such as lighting and cooling. And then it is the uninterruptible power supply, which essentially is a big battery, and it will supply the power when the main power source or utility power goes down. And then it is the power distribution unit, PDU. It will distribute the electricity from the UPS or the power source to the PDUs of lower layers and the PSUs, the power supply units. The PDUs can be freestanding or installed under the floor or mounted on a rack. And the PDUs are usually organized into a tree-like structure in the power path. Finally, it is the power supply unit, which is inside the servers and switches and other devices, and it will rectify the AC power to DC power. So data center power system is usually classified into a tier 1 to 4, depending on the power distribution characteristics, UPS, and redundancy. So in the highest tier, 99.995 uptime should be guaranteed, which essentially translates to 26 minutes of annual downtime. So to achieve this, power system has already integrated many failure handling mechanisms. For example, in tier 3 to 4 sites, which is what most of the production data centers are in, each critical load device, such as the switch and the server, has 2 power distribution paths, side A and side B. In case of failure of either one, each path has its own redundancy mechanisms. So complete circuit of data center power system is too complicated to draw in one slide. So let's just focus on the primary power path like this. And we designed PowerMan to enable the communications within the power system for management tasks. The idea of PowerMan is simple. We try to borrow the robustness and scalability of data center power systems by embedding the management network into it. The enabling technology is power line communication, and we redesign and replaces the PDUs and PSUs in the power system to establish a communication network. So this built-in PLC network is always available. It survives with the power system, and it reaches every device, and it is independent of the data plane. So deployment of PLC network also only reuses the power system wiring, so it requires no change to the room plan or floor design. Okay, here's the outline for the rest of the talk. First, we'll overview the PLC technology, and then as an example, we will build a real PLC testbed in our academic data center, and we will go over the challenges we face and which will motivate us to design PowerMan's new PDUs and PSUs. And finally, we will look at the implementation and evaluations. Okay, let's begin with power line communication. So what is PLC? We know that power line delivers electricity to the devices, and PLC is just high-frequency data signal combined with the 50 to 60 hertz AC power signal. So PLC uses the existing power lines to transmit the signals, and this is shown in both the time domain and frequency domain on the left. The PLC channel condition is known to be very challenging due to high attenuation, multipass fading, and noise. So for a very long time, the PLC have limited use cases, such as industrial control, factory energy management, and power line maintenance. And these kind of applications have a low data rate of a few kilobits per second. But recently, we have seen many advances in the device computing power, the coding schemes, and also the signal processing techniques. And this enables high-speed broadband PLC for home networking scenarios. Currently, the vendors have converged to use home plug protocols, which uses OFDM, basically is orthogonal frequency division multiplexing for the modulation scheme in the physical layer, and the CSMA-CA as the MAC layer protocol. So home plug protocol will provide Ethernet connectivity for household scenarios with up to 1200 megabps data rate in the physical layer. So this high data rate opens up new possibilities, and one of them is that can we use this to transmit? Can we use this to run data center management tasks? And we decided to build PowerMan in our own academic data center to find out whether it is possible. So in the process of building a PLC network, we encounter 2 problems. The first one is wiring, and the second one is scalability. And we design PowerMan PSU and PowerMan PDUs to solve these 2 challenges. So first, let's introduce the most important device in PowerMan, the PLC modem. They can be connected to the Ethernet ports of servers and transform the data frames to PLC signals and demodulate the PLC signals back to the data frames. So there are many PLC adapters, and we choose one with 1,000 megabps physical rate. We just purchased it from a local vendor with $30 a piece. So before we connect the PLC modems, the server has two wires, a power cable and a network cable. So we connect the PLC modem to the PDU, and each server is connected to one PLC modem using its spare Ethernet port. We can see that doing so will result in 2 times the power socket usage, as well as 2 times the network cables, which may exceed the PDU size as well as the wiring space in the rack. So in the end, this is what our PLC testbed looked like. We did not deliberately try to make it messy, but the PDU is fully loaded with servers, so we have to hang more power extension cords on the side to fit the PLC modems. So how do we handle the problem of too many wires? Our answer is to increase the integration level. Basically, we try to move the wires inside the servers. We have 2 designs of PSU for different deployment scenarios. For new data centers, we try to redesign the PSU to give it PLC networking capabilities. We do so by integrating a PLC modem as well as a NIC, so that the new power supply unit will connect to both the power connectors on the motherboard as well as the PCIe port. But in most cases, we cannot replace all the PSUs in a data center. So we also introduce a bump in the wire design, which will use the management port on the back panel of a rack server. The PLC modem will attach to the PSU externally, and it is essentially a bump in the power cable. And the power to the server is transferred to the normal PSU, the MPSU here, using a bypass circuit around the PLC modem. And then we connect the PLC modem to the management port on the back panel using a short network cable. The cable is short because the distance between the power port and the management port is usually short, and going along the back panel will prevent it from tangling with the other wires in the rack. And we try to use this bump in the wire design in our prototype, which we will see later. So by moving the cables inside, we maintain the same rack dimensions and the PDU socket count. And now the servers are PLC capable. And next, we try to connect them with the PowerMan PDUs. So can we connect all the servers in the data center in one PLC network? And we perform an experiment to find out the scalability of our PLC modems. We add PLC modems to the power strip one by one, and then verify the connection using ping utility. We observed that we can at most fit in 6 PLC modems using our current model. And when more modems are connected, only the first 6 can essentially communicate with each other. This limit seems to be imposed by the branded model, and some models claim to accommodate up to 64 modems within one circuit. But still, the scalability is quite limited, and 64 is simply too small a number for data centers. So then the question becomes, with this limited scalability of current technology, can we still reach the devices, all the devices in a data center? So our answer is to form a big network by connecting multiple smaller ones. Each PDU can be considered a smaller PLC network, and the key problem is to prevent interference between these smaller networks so that the same set of OFDM frequencies can be used in different PDU circuits. So we keep the circuits of a normal PDU and add a low-pass filter between this circuit and the upper layer power line. So the PLC OFDM frequency is above 2 megahertz, and with appropriate cutoff frequency of the low-pass filter, we can greatly attenuate the outgoing and incoming signals so that we can remove the interference between the PDUs. At the same time, we preserve the cross-circuit network connectivity by using a packet forwarding gateway, which is also integrated into the PDU. So the LPF can prevent the high-frequency signals from coming in or out. So without the cross-circuit interference, we can scale PowerMan by just connecting the PDUs together. And the PowerMan PDU also replaces the original PDU, but retains the same cable and socket count. Okay, so with the new PowerMan PDUs, we can now connect them and scale the PLC network to support real data centers by just reusing the power system wiring to interconnect the PLC devices. So the typical topology is like a tree, using a household PLC devices with 64 PLC modems inside the circuit and a 3-level tree. We can essentially connect up to 250,000 PSUs. So PowerMan leverages the redundancy in the existing power system to achieve high level of robustness. In a tier 3 to 4 data center, as we have seen just before, the PowerMan can be integrated into both power distribution paths, and the management application can have access to both sides of the power path, just like the power system does. So it will share the redundancy and availability mechanisms, and we expect PowerMan to even survive the partial power failures in tier 2 or above data centers. So finally, we will look at PowerMan's implementation and performance. We construct 3 PowerMan PDU prototypes, and this will form a tree topology of two layers. In layer 0, the prototype has 2 racks, and each rack have 5 servers and one PDU and one gateway inside the PDU. So the remaining sockets on the layer 1 PDU will connect to other servers to emulate the gateways of other layer 0 PDUs. So in total, we will have 12 servers and 16 PLC modems connected and can fully communicate with each other. This will exceed the default network size of our PLC modems by 167%. And we'll start our evaluation with some micro benchmarks. We measure the throughput and round trip time, and we vary the number of PDUs between the source and destination. So with more PDUs in between, we see lower throughput and longer RTT. And overall, the PowerMan prototype can demonstrate less than 14 millisecond average RTT and more than 14 megabit per second throughput for common management traffic patterns, many-to-one and one-to-many. This is true for the distance equal to 2, which translates to a tree height of 3. And it indicates that a PowerMan with tree height equal to 3 can provide reasonable latency and throughput for common management applications. We also want to emphasize that this is the performance achieved by household PLC devices, and in the future, for PLC modems customized for data centers and shielded power cables, we expect to achieve better performance. But for now, let's look at how this low-performance network composed by current PLC devices will affect the user experience of management applications. So we choose 4 management tasks, including a server setup, a firewall configuration, updating a service, and collection of egress rates. We compare the performance of PowerMan with a tree height equal to 1, which is everything inside one PDU, and our prototype, which is tree height equal to 2. So we can see that by adding one more layer in the PowerMan prototype, we can see 10% increase in the task completion time. Then we compare it with the electrical switch as a baseline. And we can see that the management tasks in the electrical switch have better user experience, but only slightly. And we can see the network latency is not really the bottleneck in these types of management tasks. Finally, we will compare the cost of PowerMan and the other technologies that can be used to construct out-of-band networks. And first is the component cost. At the scale of 16,000 servers, PowerMan can be constructed using only half or 1/3 of the cost of other proposals. And in terms of the deployment, because PowerMan reuses the wiring in existing power system and only replaces the PSUs and PDUs, so constructing PowerMan does not affect the room design or the floor plan, which will greatly reduce the cost compared to the other proposals. For operating cost, PowerMan consumes much lower power at the same scale, using only 6% to 9% the power of other designs. And this is because PowerMan is mainly composed of PLC modems with low power usage. And overall, we can say that PowerMan is a low-cost option for management networks. So to sum up, PowerMan is a robust, scalable, and easy-to-deploy management network for data centers. It provides necessary bandwidth and latency for management tasks, and at least it is suitable as a backup or last resort network that can be constructed with low cost and ease. And the PowerMan employs PLC technology to borrow the robustness and scalability of existing data center power systems. And we redesign PSU and PDUs to construct PowerMan with only household devices. With that, I want to say thank you, and I'm ready to take questions.
I'm not a power engineer, but the question is, does PowerMan is PowerMan compliant with standard power, with power standard, and how safe is it to use this in a data center?
Well, because we're using household PLC devices, at least it is safe in a household scenario. I'm not sure about whether it can be used in the data center using household PLC devices. But there exist multiple industrial standards for PLC communication. So later, when we design a new PLC device for data center use, we can comply with those standards. The main issue with the safety is that we can only transmit signals within some power range, so that it won't affect the other, so that it won't introduce too much noise and affect the other power circuits inside in an industrial setting, I should say. Yeah.
Okay, very nice. So I actually have a question. So
Sure.
The key idea is borrow robustness from
Yep.
the existing power system.
Right.
But you actually insert new components into the power system. Would that actually decrease robustness? But
Well,
putting that
yeah.
way, will a failure in PowerMan, any component you added for PowerMan, a failure in them would jeopardize the original power system's availability?
Yes, it is a possibility, and the main issue here is the low pass filters in the PDUs, and we need to make sure that the low pass filter is up to some standards and will not fail that easily.
Right, but the thing is are multiplicative, right? Even if your filter has 99.999% of availability, if you add, let's say, 5 of them, basically would decrease availability significantly, right?
Yeah. So the question still is, will PowerMan affect the robustness of data center power systems?
Right.
But as I know, the low pass filter is essentially surge protection circuitries. And surge protection circuitries protects the power circuits from lightning strikes and things like that. And basically, lightning strike is basically a high frequency signal with large power. And surge protection is already in place to prevent such event from happening. So we can see that the surge protection circuitry is already robust enough to be integrated in the existing power systems. And we can still use that surge protection circuitries as the low-pass filters, as we did in the prototype implementation.
But okay, we can take self.
Sure.
Any other questions? All right. Okay, that concludes this session. Let's thank our speaker again.
Thank you.